Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at setting up a basic Kubernetes cluster on cloud VMs, GCP in this case, for learning purposes.
Yeah, so if you've ever wondered why, clicking deploy on a managed cloud Kubernetes service takes maybe 10 minutes, but building it yourself from scratch takes days of hunting down weird kernel routing bugs, well, today we are taking away the cloud provider's magic wand.
We really are. No one-click deployments today, no hidden control planes doing the heavy lifting for you.
Exactly. We are taking a stack of raw architectural notes and building a highly available multi-node cluster completely by hand.
Though before we get too deep into the actual architecture, we really have to establish a strict boundary for what we are building here.
Right, the caveat.
Yeah, the setup. The topological design we are executing today is fundamentally sound for high availability, or HA. You have redundant control planes and a load balancer. But the physical footprint is sized strictly for learning.
Yeah, we're using pretty lightweight virtual machines here.
Exactly. Micro and medium instances. If you were deploying a true production environment for, real user traffic, those workloads would require significantly more CPU, memory, and specialized storage classes than what we're provisioning today.
Right, so we are building a perfectly functioning scale model, basically, not a real skyscraper.
That's a great way to put it, yeah.
So let's look at the raw materials on Google Cloud Platform. We are operating inside a dedicated project called K8's project, and that's wrapped in a virtual private cloud network named K8's Network.
Which is just a standard VPC setup.
Right. And within that VPC, we carve out a single subnet at 10.22.64.024.
And that specific Class C subnet block is actually really important. It gives us over 250 available IP addresses.
Which seems like a lot for just a few VMs.
It is, but that's plenty of breathing room for the actual physical virtual machines we're about to deploy.
Yeah.
While leaving a massive non-overlapping space for the internal cluster IP addresses, because Kubernetes will eventually assign its own IPs to services and pods.
Right. You never want your physical network IPs colliding with your virtual container IPs. That's a nightmare to debug.
Oh, absolutely.
So as for the hardware itself, we are spinning up 6 virtual machines in total.
Okay.
We have one E2 micro instance with a static IP, and that's acting as our management VM. Then we are provisioning 2 E2 medium instances to serve as our control nodes.
The brains of the operation.
Exactly. And finally, 3 more E2 medium instances for our worker nodes. Every single machine is running a 20 gigabyte standard persistent boot disk, and they are all loaded with the Ubuntu 24.04 LTS minimal image.
And that choice of the minimal image is very intentional here.
It's the bloat.
Right. A minimal operating system gives you a vastly reduced attack surface. You have, fewer background services competing for compute cycles and fewer open ports to worry about.
Makes sense.
But the trade-off for that security and efficiency is that the OS is incredibly bare bones. Yeah. Like if you tried to install Kubernetes directly onto these fresh VMs right now, the system would just violently reject it.
Yeah, and I kind of love that. It's a perfect analogy for the reality of distributed systems. You don't just install software like it's a desktop app.
No, you really don't.
You have to fundamentally mutate the underlying Linux environment so it can actually handle the bizarre networking and storage demands of containers. So I sort of think of this phase like surveying a plot of land and laying down all the underground utility pipes.
The VPC and subnets, right?
Yeah, exactly. You have to lay the pipes before you can drop down the concrete foundations, which are the VMs themselves. So, first rule of this phase. These baseline OS preparations apply to every single node.
Uniformity is key.
Right. We start by pulling the latest repositories and upgrading the minimal Ubuntu packages so we aren't inheriting, day one vulnerabilities. But once the system is patched, we run into our first major architectural hurdle.
DNS and networking.
Yeah. And the source notes dictate a very specific step here. We use a command, hostname-i, to retrieve the primary IP address of each node. Then we manually append that IP address and the node's hostname directly into the echoes file on every single machine in the cluster.
I know what you're going to say.
Wait, hold on. I have to play devil's advocate here for a second. Hard-coding static IP addresses into an echoes file in 2026.
It sounds bad, I know.
If we are building a modern cloud-native distributed system, why are we utilizing a server management trick from, 1995? In any normal cloud architecture, that is a massive anti-pattern. You want everything dynamically resolving through a dedicated internal DNS server so the infrastructure can auto-scale, right? without human intervention.
In a dynamic, auto-scaling production environment, you are absolutely correct. Manual hosts entries would be an operational nightmare.
Right, so why do it here?
Well, here is the mechanism behind why the sources mandate this for building a cluster entirely from scratch. You are dealing with a classic bootstrap chicken and egg problem.
Okay, how so?
Kubernetes relies on an internal DNS service, usually core DNS, to route its internal traffic. But core DNS actually runs inside the cluster as a pod.
Oh, so how do the nodes communicate to build the cluster before the cluster's internal DNS even exists?
Precisely. During that initial bootstrapping phase, the kubelet agent on each node is desperately trying to establish a connection with the API server.
And if it can't resolve the name?
Exactly. If it relies on an external cloud provider DNS that experiences even a momentary blip, the bootstrap fails. So by hard-coding those paths in echosts, you completely remove the external dependency.
Ah, okay, I see.
You are provided the kubelet with a rock-solid, unshakable local map of where every peer lives. You temporarily trade dynamic scalability for absolute deterministic reliability during the most fragile 5 minutes of the cluster's life.
Okay, wow, that makes perfect sense, actually. You just bridge the gap until the cluster can host its own intelligence. Okay, so the nodes can confidently find each other. But finding each other isn't enough if they start fighting over hardware resources. Which brings us to swap space. We run commands to permanently disable swap memory on all nodes.
Yeah, and the relationship between Kubernetes and swap space has a really fascinating evolution.
Because it used to be strictly forbidden, right?
Historically, the project strictly forbade it. The entire philosophy of the Kubernetes scheduler relies on having a predictable, mathematically precise view of memory resources. It needs to know exactly how much RAM is available to place a pod on a node.
Because if a node runs out of physical memory and starts silently paging data to a wildly slow hard drive, the scheduler has no idea that performance just fell off a cliff.
Exactly. The scheduler operates on the assumption of failure. It would much rather aggressively kill a misbehaving memory hogging pod and restart it elsewhere than allow one pod to force the entire node into a swap death spiral where all services just grind to a halt.
Yeah, that makes sense.
However, the ecosystem is shifting a bit. In Kubernetes version 1.34, node swap support officially graduated to general availability.
Wait, really? So you actually can run swap now?
You can, yeah. But it requires incredibly strict, tightly controlled cgroup v2 configurations to isolate exactly how that swap is used. It is a major philosophical pivot for the project.
But I'm guessing we aren't doing that today.
No. For the sake of our specific architecture today, the Ubuntu minimal cloud image actually ships with swap disabled by default anyway. We just verify the state and move on to the kernel.
Good. The kernel is where the real illusion of Kubernetes happens anyway. We have to manually load two specific Linux kernel modules, Brunet filter and overlay. Let's look at the networking side first. Why is Brunet filter non-negotiable?
So think about how containers operate on a single machine. They usually share a virtual Linux network bridge to talk to each other.
Okay.
Normally, the Linux kernel doesn't pass that internal bridge traffic through iptables, which is the system's firewall and routing tool. But Kubernetes relies entirely on iptables to implement its complex service routing.
Ah, so it needs to see that traffic.
Exactly. The Brunet filter module essentially forces the kernel to intercept that bridged container traffic and hand it over to iptables for processing. Without it, the kube proxy component is entirely blind, and your internal network routing silently fails.
Right, and we also configure sysctl for IPv4 and IPv6 packet forwarding at this stage too, right? So the node actually knows how to forward those intercepted packets.
Exactly. sysctl is vital for enabling that IP forwarding.
And then the overlay module handles the storage illusion. Because when you deploy a container, you aren't just downloading a massive single file. You are pulling down an image composed of multiple read-only file system layers stacked on top of each other.
Crowned with a thin read-write layer for the active application, yeah.
Right. And the overlay kernel module is the specific technology that allows the operating system to smash all those separate layers together and present them to the container as one unified file system. Without it, your runtime physically cannot unpack or run an image.
And speaking of that runtime, we actually have to install the engine that pulls those layers and starts the processes.
Because Kubernetes doesn't actually run containers itself.
Right. It delegates that via the Container Runtime Interface, or CRI. Our sources outline the major players here. You have standard Docker engine, which now requires a clunky translation adapter called cry-dockered.
Yeah, we want to avoid that if possible.
Then there's CRIO, which is fantastic but closely tied to the Red Hat ecosystem. And finally, containered.
We're going to go on with containered. It is fascinating how it evolved, actually. It used to just be a core component buried inside Docker.
Yeah, it was.
But the community ripped it out, stripped away all the developer-friendly desktop tools, and turned it into an incredibly fast, highly stable daemon whose sole purpose in life is managing the container lifecycle. So we add the repository, download the signing keys, and install it on every node.
Which leaves the final step of OS preparation, installing the Kubernetes binaries themselves. We add the repository for version 1.35 and pull down 3 critical packages.
Okay, hit me.
First, you have kubeadm, which is the bootstrap utility that actually orchestrates the cluster creation. Then you have the kubelet, the primary agent that runs on every node and listens for orders. And finally, kubectl, the command line tool you use to interrogate the API.
But there is a massive trap here if you aren't paying attention. Once those 3 packages are installed, the sources mandate using the apt-mark hold command to lock their versions in place.
Oh, yes. If you want to see a cluster tear itself apart, skip that command. Kubernetes is highly allergic to severe version skew between its components.
Oh, I've seen the postmortems on this. You build a stable cluster, everything is fine. Then 2 weeks later, the Ubuntu unattended upgrade service wakes up in the middle of the night.
Always in the middle of the night.
Always. It sees a newer version of the kubelet in the repository and automatically patches it on your worker nodes. But your control plane is still running the older kubeAPI server version.
And boom.
Yeah, the workers suddenly can't communicate properly with the brain, the API requests fail, and you wake up to a completely degraded environment. And you're just sitting there digging through systemctl and journalctl logs, trying to figure out why the kubelet is crash looping.
Exactly. The apt-mark hold prevents the OS from ever touching those binaries without your explicit manual permission.
That is the essence of building from scratch, really. You have to anticipate what the operating system will do when you aren't looking.
You do. So the foundation is completely set. Every node is uniformly patched. The kernels are manipulating packets. The runtimes are standing by, and the binaries are locked.
It is time to introduce the traffic cop. We have that single E2 micro virtual machine sitting off to the side, our management node.
Right.
We install HA proxy onto it, pulling down the extra packages since it's a minimal OS. But why introduce a separate load balancer into this architecture at all? Why not just have the worker nodes talk directly to the first master node?
Because of our primary goal. High availability. We are going to have 2 control plane nodes.
Right, the redundancy.
Exactly. If a worker node or an administrator using kubectl points their request directly at the IP address of control node 1, and that node suffers a kernel panic and dies, the entire cluster becomes unmanageable.
Because the requests are just hitting a wall.
Right. It doesn't matter that control node 2 is perfectly healthy, the traffic is hitting a dead end.
So aproxy operates less like a simple intersection traffic cop and more like a triage nurse at an emergency room.
Oh, I like that.
Yeah. It isn't just blindly pointing cars down a road.
Yeah.
It actively sits in front of the control plane and constantly performs liveness checks on the QAPI servers. When you send an administrative command, the triage nurse evaluates which master node is actually healthy and capable of receiving a patient and instantly routes your request through those double doors.
Exactly. That single static IP address belonging to the hproxy machine becomes the ultimate endpoint for the entire cluster. Everything talks to the load balancer, and the load balancer abstracts away the complexity of the redundant control planes behind it.
Okay, the triage nurse is standing at the desk, but the hospital is completely empty. We have to wake up the first control node.
Time to build the brain.
Right. We log into our first master VM and execute the kubeadm and init command. And crucially, we explicitly tell this command to use the aproxy IP address as the main control plane endpoint.
Right, and when that command finishes, the API server comes online, the scheduler starts up, and the node registers itself. But if you run a command to check the status of the cluster right then, that brand new master node will flatly report its status as not ready.
Which feels like a failure when you first see it, but it's totally expected.
It is.
The core Kubernetes components are running, but the node is paralyzed because it lacks a container network interface, or CNI. In our blueprint, we are deploying the Calico CNI. But I have to push back again here because this is where cloud networking gets really confusing.
Okay, lay it on me.
We spent the very first step of this deep dive building a virtual private cloud on GCP. Google's infrastructure is already perfectly capable of routing packets between these virtual machines. Why on earth do we need to install a massive, complex secondary network like Calico on top of an already functioning network?
It's a great question. And it's because the GCP network understands how to route traffic to your virtual machines, but it has absolutely no idea what a container is.
Ah.
Remember that Class C subnet we carved out? IP exhaustion is a real threat here. If you relied on Google Cloud's native VPC to assign an IP address to every single pod that spins up, you would deplete your cloud network space instantly.
And your cloud bill would be absolutely chaotic.
Exactly.
So you need a layer of abstraction.
You do. Calico creates an overlay network.
Yeah.
So, I like your earlier hospital analogy, but let's pivot to a corporate office for a second.
Okay, sure.
The GCP DPC is the National Postal Service. It knows how to drive a truck to the physical address of the office building, the VM. But the National Postal Service doesn't know who sits at desk 4B on the 3rd floor.
They just drop the mail at the front desk.
Exactly. Calico is the internal mailroom. It manages a massive, completely internal pool of IP addresses just for the pods.
Yeah.
It uses protocols like BGP or IP encapsulation to ensure that when a pod on node A wants to talk to a pod on node C, the packet is wrapped up, sent across the GCP network, and perfectly unwrapped and delivered to the correct container on the other side.
Wow. That is a perfect analogy. The internal mailroom. And it handles all the security policies too, right? Dictating which pods are even allowed to talk to each other.
Yep, all of it.
And the second that internal mailroom comes online, the master node transitions from not ready to ready, we finally have a functional thinking brain. But a single brain in a distributed system is a terrifying single point of failure.
It is, which is why we immediately moved to synchronize the second control node. And this is a very specific high-stakes procedure. You do not just run a basic join command here.
Right, you have to join the new master node using the QBADM join command with 2 very specific flags, control plane and certificate key.
Yes. Let's break down the mechanics of why that matters. Why is adding a second master so much more complex than adding a standard worker node?
Well, because of the split brain problem, right?
Exactly.
When you have 2 master nodes, they both want to dictate the state of the cluster. To prevent them from corrupting the environment, they have to share a single source of truth. And in Kubernetes, that source of truth is a distributed key value store called etcd.
And etcd doesn't just trust anyone. It requires cryptographic proof.
Right. And if you really need to debug that database, you're usually using etcdctl or etcdutl directly. But to expand the control plane, you first go to your existing healthy master node. You run a command that generates a fresh bootstrap token and uploads the latest cryptographic certificates to a secure secret.
Right, a 2-step dance.
Yeah. You take the massive certificate key string it spits out, and you feed it into the QBADM join command on the new master. That flag essentially says, I am not just here to run workloads. I am here to manage the cluster. And here is the exact cryptographic key required to decrypt the EATCD database and synchronize state.
It's beautiful, really. Once that synchronization happens, your architecture is fundamentally transformed. You now have true redundancy.
It's no longer a toy.
No, it's not. If Google Cloud experiences an underlying hardware failure and abruptly reboots your first master node, the triage NERSA proxy detects the dropped connection instantly.
And it redirects all new kubeAPI requests to your second master node.
Exactly. Your administrators keep working, the cluster keeps routing traffic, and the environment barely blinks.
It is a brilliant piece of engineering. But a highly resilient brain with nothing to control isn't actually executing any business logic. We need the muscle. We have 3 E2 medium worker nodes just waiting for instructions.
And after the complexity of the cryptographic control plane synchronization we just did, adding worker nodes is almost laughably simple.
It really is. Because we did all that painstaking OS preparation up front, attaching the workers simply requires executing the standard QBADM join command on each of the 3 worker VMs. No certificate keys, no control plane flags.
Just the basic token.
Yeah, you just provide the token, and the kubelet reaches out to HA proxy.
And this is the moment where every seemingly tedious step from our earlier OS preparation finally clicks together.
The payoff.
Yes. The instant that worker node authenticates, the Brunet filter kernel module wakes up and begins intercepting packets. The containered runtime receives its first deployment manifest from the API server and begins unpacking the overlay file system layers.
So your Nginx container finally spins up, for example.
Exactly. And then the Calico CNI assigns the pod a dedicated internal IP address, and the workload goes live.
It is incredibly satisfying to see it all spin up. So let's recap the reality of what you've accomplished here today. You didn't just rent a managed service.
No, you built it.
You started with a blank GCP network. You meticulously prepared the underlying Linux kernels to handle container routing and storage. You built an aproxy triage nurse to monitor health.
And you synchronized a distributed etcd database across redundant master nodes using cryptographic keys.
Exactly. And you deployed a Calico overlay network to manage internal pod communication across your worker pool.
You built a complex distributed system from first principles. And that's huge, because when things inevitably break in the future, when a network route drops or a pod can't resolve a service name, you won't be staring blindly at a managed cloud dashboard waiting for support.
Right, you know exactly how the packet flows, you know where the certificates are stored, and you know why the kernel modules actually matter. You own the stack.
You really do. But before we wrap up, this architecture leaves us with a compelling puzzle to consider. Yeah, you have engineered a bulletproof control plane, and you have a network of eager worker nodes. But what happens to the internal state of your actual applications when the underlying cloud provider inevitably reboots one of those worker VMs without warning?
Ah, the chaos of the cloud.
Right. The cluster architecture survives, yes.
Right.
But how do you design your software so that your workloads survive the absolute chaos of ephemeral infrastructure?
Now, that is a perfect question for your next microservice design session. Thanks for joining us, and we'll catch you on the next deep dive.